inviting me to come here. I haven't been to a meeting on F-theory. It's my first time, I suppose. So I will present some results that we have which are field theoretic. I will present it in a field theory, and what I want is to give it as a challenge to the F-theory community, such that when you construct those gauge theories using F-theory, you'll look for the phenomena that I'm going to mention. Now, let me start by talking about the Higgs branch. Today, what we do is to talk about Higgs branches in 6 and 5. And we will have a theme that we are going to ask. And we are going to first say some few words about Higgs branches. Unfortunately, Higgs branches are not well studied. They are possibly thought to be too simple to trivial, no quantum corrections. But today I'm going to say that this is not correct. This is a wrong perception. Higgs branches are said to be not corrected at, as a function of the coupling. And this is almost correct. And the thing is that if I tune the coupling to be a finite value, then the Higgs branch does not depend on the gauge coupling. But if I send the gauge coupling to two extremes, either to 0 or to infinity, then the Higgs branch changes. So this is not at infinite coupling. We get a jump. The Higgs branch is different. And I want to get a quantitative understanding of how different it is. So the question that we are going to ask is to take some theories. We will take some gauge theories and compute this quantity, h infinity. And I'm going to ask this question in 5 dimensions, and I'm going to ask this question in 6 dimensions. Now, the phenomena in 5 and 6 dimensions are very different. In 5 dimensions, if I set 1 over g squared to 0, 1 over g squared has a scale of a mass, and I'll get new massless states. So there will be new massless states. These massless states are gauge instantons. And those are going to do 2 things. One is that I'll get symmetry enhancement. And the second thing is that new flat directions. And in total, the Higgs branch is going to contain the Higgs branch finite coupling, and I want to understand precisely how. Okay? In 6 dimensions, on the other hand, I'm going to do the same thing. Now 1 over g squared has the scaling of a tension of a string, and so I get tensionless strings. And actually, I'm going to get infinitely many massless strings. All of the modes of the string of a zero tension are going to become massless. But nevertheless, even though these are infinitely many, I want to understand what happens to the Higgs branch. The Higgs branch doesn't go by a lot. So the dimension of the Higgs branch can grow. But if it grows in some fixed unit, by 29, for example. In which case, this is going to be the small instanton transition. Or it could stay the same, but still be different. So how different is it going to be? Now, this type of questions could have been asked many years ago. This is a long-standing problem. First of all, the misconception that Higgs branches do not change. This has been there all along. If I ask here questions about Coulomb branch, I'll get many answers about Coulomb branches, but very few answers about Higgs branches. The second point is that, we didn't have really much tools about understanding strongly coupled phenomena in 5 and 6 dimensions, and this is going to change. Now, how typically do I compute a Higgs branch? A Higgs branch note Higgs branch at finite coupling, computed by solving the hyperkähler quotient. Hyperkähler quotient, and this amounts to taking F terms, D terms, and looking for the solutions of such moduli spaces. Now, the thing which happens at 5 and 6 dimensions is that I no longer have a Lagrangian. I get a super conformal field theory. I don't have a Lagrangian, therefore I cannot write F and D term equations, and I cannot answer this question, H infinity, typically is not hyperkähler quotient. However, it is still a hyperkähler cone. And as such, I can think of other ways of constructing such a moduli space. And this is where the physics of three-dimensional gauge theory gets into the game. So I can construct it as a Coulomb branch of a 3D gauge theory with 8 charges. Okay, and so that's a new point. This is a point which was not so taken into account seriously. And if we do begin to take this into account, then we get some set of beautiful results. So I'm going to construct this Higgs branch at infinite coupling for some theories using a Coulomb branch of a three-dimensional theory. Now, there are two important features about Coulomb branches of three-dimensional gauge theories. There is an SU, which is there whenever I have a hyperkähler moduli space. it acts on the 3 complex structure. And if I have a global symmetry in the gauge theory, it's going to commute with this SU2R, and I'm going to have fairly large global symmetry. I'll call it F for flavor. Now, these are the isometries. These are the symmetries of this space. And any operator, any observable, is going to transform under these 2 representations. Now, there is a generic question of what I need to do, how much is needed to construct such a space. And one of the points, the main points, is that not much. Hyperkähler is restrictive enough such that if I know the global symmetry and few other features, then I can construct the whole space. It's really magical. The global symmetry dimension and few representations under those symmetries. So this is our task, and let's do a simple case, 6-dimensional theory. So Alessandro was telling us about not so much about 6 dimensions, but he got the gauge group that I want. So let's do it. So it's going to look like a quiver, SP K minus 4 gauge theory with SO 4K. Right, so it's a simple gauge theory, SQCD. It's from the family of SQCD. The gauge group is symplectic. The flavor group is orthogonal. And this is the theory which arises on the world volume of 1 and 5 on a C2 mod dk singularity. Now, this theory has a gauge coupling. The moduli space at finite coupling is just a nilpotent orbit. How many people know about nilpotent orbits? This is a math audience. Not so many. Oh, a few more. Okay, I see. So it's one of the nilpotent orbits. I'll give you the data here. It's 2k minus 4, 1 to the 4k minus 2 times k minus 4. But I could also give some algebraic description. It's just the set of all 4k by 4k matrices such that they are antisymmetric and they square to 0.
Maybe you write it somewhere else? Or no, put it up. Or put it up.
Put it up.
No, no, yeah.
Put it up. Okay. Just a little bit. M squared equals to 0. Thank you. M squared equals to 0, and the rank of M is at most 2. Nice algebraic variety, not too hard. This is the moduli space. I can use, since it's a finite coupling moduli space, I can just use F and D term equations to compute this. Now, what happens when I set the gauge coupling to infinity? The global symmetry remains the same global symmetry. And this is something that is related to this comment over here. I'm trying to pick some data, pick some clues about what happens to this moduli space, and then to set it exactly, right, to determine this thing exactly. So the moduli space remains the global symmetry remains the same, except for an exception at k equals to 4, where we will see it's going to turn as an E8 symmetry, but at the moment I didn't explain why such a system will become E8. One thing you could see is that there is an SO16 here, and this SO16 is going to become E8. So there's a missing spinor somewhere. Now, the other point which happens when I set the gauge coupling to infinity is that I have new states on the tensionless string. And this can be viewed as you could take the gauge instanton of this theory. It carries tension, which is 1 over g squared. Or alternatively, pick your favorite construction of such a gauge symmetry, and then look for the BPS string, which is there. So for example, in the, if I'll have an O6 minus plane here with K D6 brane, and there are 2 NS branes over here, then over here, the tensionless string, the BPS string is the guy here. It's a D2 brane, which is stretched like that. And it has a tension proportional to this distance between the branes. Now, in this system, I do get a jump by 29. The Higgs bunch becomes larger. And this we can just see by anomaly cancellation. So the dimension grows by 29. You see, those are not allowed to move away from the orientical plane. Those are half M5 branes. They are stuck. However, when I go to the tensionless limit, they can coincide and move apart. At this point, I lose 1 tensor multiplet in this system, and as a result, by anomaly cancellation, I gain 29 hypers. So the Higgs bunch goes by 29, and I want, thank you, and I want to figure out what this space is going to be. Now, here, let me point something in 3D Coulomb branches. This is a very important theorem which leads to the computation that we're going to see. So for a quiver, the subset of balanced nodes forms the Dynkin diagram of the global symmetry. This is a very important point, because if I know what is the global symmetry, I can construct a quiver and then compute its Coulomb branch and get the right moduli space. So let's do it. We have only 10 minutes, so I'll just do it. I'll take a global symmetry SOK. The Dynkin diagram is D2K. And a notion of balance of a node means that the number of neighbors, or the total sum of ranks, is twice the rank. So as an example, if I construct, here's a part of a Dinkin diagram. If I set the first node to be 1 and the second to be 2, then this node is balanced because its neighbor, there is only one neighbor, and it has node number 2, and it's twice the number 1. And now, in order to make this balance, I'll put a 3 here. Now, 3 plus 1 is twice 2. And in order to balance this, I'll put a 4. 4 plus 2 is twice 3, and so on. I can balance it one by one. And I'll go all the way up to D 2k minus 3, and another one 2k minus 2. Next, I'll add, I'm dealing with the D2k. So I need one spinor node. And in order to make this spinor node balanced, I'll put k minus 1. Right? Now k minus 1 is balanced. But this one is not balanced, so I'll put one more node. And I'll balance it. So this should be k, just k. Okay? So now this one is balanced, but this is not. So in order to balance this, I'll put a 2. So here I constructed a Dinkin diagram such that all nodes are balanced except for the last one. I'll denote it by red, like this. This is the only node which is unbalanced. Okay? And now my claim is that the 3D Coulomb branch of this quiver is equal to the Higgs branch at infinite coupling of the theory we started with. Okay? There is an imbalance to the quiver. And so you see, just this thing here and the knowledge of the global symmetry allow me to construct a quiver such that all nodes are balanced except for one. But the nodes which are balanced form the Dinkin diagram of D2k. Okay? So the global symmetry allows me to construct such a quiver. Now we know this, I don't know if you heard the talks about Coulomb branches of 3D gauge theories, but given such a quiver, I already know the moduli space. It's just an action of a set of technical operations which we now excel. We can produce many such things. If you give me a quiver, I can tell you what is the corresponding Coulomb branch. So it's equivalent to what we said before. Knowing F and D term equations, I know the Higgs branch of hyperkähler quotient. Knowing the quiver, I can construct the Coulomb branch. I don't have the time to explain this, and this is a very interesting thing. Maybe I should mention that the key is to understand monopole operators. However, let's look at the node which is not balanced. Actually, it's only balanced if I set k to be equals to 4. So if I'm taking k equals to 4, then, oh, did I write here 4? I'm sorry for this. This is a big k, not 4. So if I take k equals to 4, I do get the D4 singularity. And for k equals to 4, what I get over here is the balanced Dinkin diagram of affine E8. It leads to, thank you, E8 enhancement, and it also leads to a moduli space. Now let's check this growth by 29. When k is equal to 4, I have no gauge group here, and so there's no Higgs branch. It's just a point. It's going to be a trivial space. On this quiver, on the other hand, if I sum the total number of ranks, I'll get 29-dimensional. So the moduli space of the Higgs branch at k equals to 4 is just the minimal nilpotent orbit of E8, or otherwise known as the moduli space of one E8 instanton on C2. What about this imbalance? The imbalance here, so imbalance is k minus 4. It's just the number of flavors. Number of neighbors is k, and I subtract twice 2. So it's proportional to k minus 4. For k equals to 4, we saw that the node is balanced. For k higher than 4, it's not balanced anymore. Okay? And so this imbalance leads to a state in the ring. So I have a hyperkähler moduli space. There is a ring. So the state in the ring will be in the spinor of SO4K and in the representation k minus 2 over 2 C2R. And I, again, don't have time to explain, but this is something I can read off the quiver. And so my moduli space is going to have two special objects. One is the adjoint representation of SO4K. This is the thing which gives me the global symmetry. And the second one is this guy, spinor representation. Where does it show up? The most basic object which lives on this tensionless string is in the spinor representation. Okay, we're out of time, so let me try to show one last thing, and then we will stop. Let's try to understand this difference of 29, and I will call it quiver subtraction. I'm going to take this quiver over here and subtract the affine E8 Dynkin diagram. I'm just going to subtract this. And so let's do it node by node. So 2 minus 2 is going to be 0. So I'm going to have nothing. K minus 4 will give me a node with k minus 4. 2k minus 2 minus 6 will give me 2k minus 8. And k minus 1 minus 3 is going to give me k minus 4. Now, here there is a node of 5. And here I have a node of 2k minus 3. So 2k minus 3 minus 5 gives me 2k minus 8 again. And I'm going to continue like that. It's the same kind of node. It's going to show 7 times. Very special number, 7 times. And I'm going to have one addition. I don't have the time to explain why this one shows up, but from this point onwards, it's going to become 2k minus 9, 2k minus 10, all the way down to 1. So this is the quiver. If I now compute the 3D Coulomb branch of this quiver, it's going to be the Higgs branch at finite coupling of the SPK minus 4 SO4K theory. And actually, what we have done is an operation on Coulomb branches. We just subtracted 2 quivers, but this operation has a geometric interpretation. It tells me that this space, HF, is included in H infinity, where there is a notion of a transverse slice. And this transverse slice is given by the Coulomb branch of this theory, which is the minimal E8 moduli space. Okay, I'll summarize by this, and I'll finish by this. Let's make a summary. So what we've seen today is, this is a new idea, relatively new. You're invited to look at our papers. We can solve problems at infinite coupling. In particular, we know how to understand Higgs branches when we tune the gauge coupling to infinity, this should have an interpretation in corresponding F-theory various model buildings. Just construct it, look for the tensionless string, set it to 0 tension, and try to ask this question. If you want, I can give you many more examples. I didn't have the time. And the key point of this progress that we have is that instead of looking for Higgs branches as hyperkähler quotients, we are looking for them as 3D Coulomb branches. And the features of 3D gauge theories allow me to construct the modularized spaces very easily. I just need to know global symmetries, dimensions, other few quantities, and that's it. Okay? Thank you. Yes.
So for k equal to 4, there everything collapses and you get 0, no?
That's right. Yes.
So everything is transverse to 0,
It's
basically.
just a point.
The point, yes.
The point, and so inside the minimal orbit of E8, if you ask what is
transverse to a point, yeah, it's
everything
everything. Okay.
transverse to a point.
And the second question I have is, how do you know that there are no multiple Coulomb branches in 3D that just go to the same type of geometry?
It's an excellent question. So this global symmetry is actually quite restrictive, and I didn't have time to cover this. You need to come up, so once you come up with a guess, you could test it, and you could check it with various dimension formulas or the minimal states that could show up. Luckily, you have to pick your problems right. If you pick the relevant theories, then the answer is actually unique, and you just get the result like it is. But I can give you a collection of tests that we can do to show it. Right? So, given a guess, you could always check whether it's consistent or not, and all of the tests that we have so far are.
These tests are what?
So the first test is the dimension. The second test is the construction of operators with which become massless on the tensionless string. If you are in 5 dimensions, you have instanton operators. You could construct the instanton operators as objects using an independent construction and check it with what you get. And it's in the papers.
Okay.
We just went over those. Yes.
I didn't quite understand if the dimension of the modular space is an input or an output. So if I give you a 6-dimensional theory with some random 6-dimensional theory and ask you the dimension at the infinite coupling point, is that an output of your construction? Is it?
I'll have to look at the theory and check whether this is an input or an output. But for this case,
because I mean, do you only look at this?
For this case, I have it. I have this thing, and so I can tell you that.
No, I understand. Yeah, but at the end, you seem to be making a more general point. If I understood correctly, you said, give me the dimension, give me the flavor symmetry, I can construct the space for you.
It's like putting pieces to a puzzle. You just look for enough pieces in order to construct the whole picture. And when I said this, I just need to look at an example to see what I know about this example and to see whether this is sufficient to determine the moduli space uniquely. Many times, the information that I need to know is just the global symmetry and the representations of the lowest lying states. And that's it. In this case, If you're asking about this case, I could argue that there is a state in the spinor representation, and that the global symmetry is this.
From the Bain diagram, you mean?
Yeah, it comes from.
Yeah, but what if you don't have any perturbative realization, but only an F-theory one?
I think those states will be there. So there are string states which go between the D2 and the D6 brane over here. So these states should be in any picture, any construction of the theory.
No, I meant for a theory which has some exceptional gauge group, or you know.
That's a good challenge. I'll have to look at it. So far, I looked at M5 living on D4 singularity, A5 living on A-type singularity. Those are the 6-dimensional models. I also looked at 5-dimensional theories, various gauge coupling, various theories with the gauge coupling going to infinity. But I'm sure that this is not the only set of theories. There's another set given by those theories which live on background with the M9 wall. So also there, it's possible to determine the gauge theory. I can show you the details.